Hello. Today I'm going to be presenting this paper on whether large language models can transform natural language intent into formal method postconditions. So let's get started. All right, so start with the content of the paper, then a bit of background, the problems and challenges, the main idea, some prompting information, evaluation information, then the results in the testing. Then I'll talk a little bit about related work and the limitations of the paper, and then I'm going to do the conclusion. All right, so the objective of the paper is, again, to translate natural language documentation into formal postconditions for methods. And we're specifically looking at the intent behind the natural language. The way they do this is they use a variety of LLMs and prompting strategies, and they evaluate it by testing postconditions with correctness with respect to valid inputs, with mutation testing, with buggy code data sets, and with real-life examples. All right, so just a little bit of background here. A postcondition is a condition on the output of a method that must hold true. So it's a subcategory of method invariants. So for this little example here, we need to remove duplicates from a list. So a possible postcondition would be to assert that all of the count of the numbers in the output list should be 1. But postconditions help with detecting bugs, they aid with debugging, and they can be used and generated alongside LLM-generated code to increase trust, especially if it's generated by the LLM at the same time. So it actually turns out that 98% of GitHub repositories have natural language documentation, and 20% of artifacts in these in all repositories are dedicated to documentation. So there's a lot of potential here if we can harness this natural language to strengthen the trust and security of these code bases. So the current methods, such as Daikon and Toga, which are the baselines actually for this method, they're heuristics based and limited, which I'll talk about when I talk about them. And also, LLMs can translate natural language to high quality code already, so extending that to generating postconditions isn't too far of a leap. All right, so some problems and challenges. First thing is that going from intended behavior to the behavior of the implementation can be difficult, mainly due to the fact that there's ambiguity in natural language, right? And I'll go over this in a second. There are also different metrics for success, especially when we're evaluating something kind of qualitative like natural language. So the authors actually bring up, or they create novel metrics for for evaluating this approach. Again, existing approaches are weak. Prompting can be an issue, and it's also a limitation, which I'll talk about later. Risk of data leakage is also a limitation, which I'll talk about later. And there's also limited training data. There isn't much training data on creating postconditions from a reference solution with natural language comments. And so a traditional machine learning approach would be difficult for that. All right, so going back to the example we saw before, where we remove duplicates, the docstring is a little bit ambiguous. So from a list of integers, remove all elements that occur more than once. So do we remove all the duplicate elements, or do we keep one and remove all of the other duplicate elements? So it turns out the developer intent for this one was the former. And so the first postcondition here, where the number of unique numbers in the input and the output should be the same, that's not a correct postcondition. All right, some metrics that the paper uses. This is natural language descriptions of the metrics. So the first one is correctness. So does the postcondition work for every legal input of the function? And this is a necessary condition, but it's not sufficient because the postcondition could just return true for every input. And so we need a completeness, which is the sufficient condition. Can the postcondition distinguish correct implementations versus incorrect implementations? And this is going to be done through mutation testing, and correctness will be done through running a regression suite. All right, so the first research question of this paper is, how well do LLM-generated postconditions formalize informal natural language intent? So that's basically what we've been talking about the whole time. The second research question is, is this applicable? Can this be applied to real-world scenarios and real-world bugs? All right, so again, the main idea, we've heard this before. LLM should act as a bridge between the natural language docstrings and the formal postconditions. What's important here is that we're relying on the emergent abilities of LLMs. So I mentioned in the problems and challenges that there isn't a lot of training data, very limited training data on this translation process, and LLMs have shown these to show abilities on tasks they weren't trained on, which is emergent abilities. So we're going to try to utilize that in this approach. The output should be language agnostic or as language agnostic as possible. So obviously not pseudocode because it should be executable, but it shouldn't depend on very niche language libraries or tools. Also, we will evaluate them with the novel metrics. So the paper tests this with GPT 3.5, GPT-4, and StarChat on a Python bugs dataset and a real-world Java bugs dataset, and I'll introduce them later. All right, so for the prompting, again, the goals should be chat-based queries, agnostic to the programming language, and directly executable. For the strategies, they have 4 total combinations, so they either include the reference solution or they don't, and they either have a simple prompt or a complex one. So this is the prompt. In green is whether they include the reference solution, and in yellow is whether they specifically ask for a simple prompt, for a simple post condition. And they added this simplicity toggle because they noticed that often the LLM would just spit out an actual implementation of the function. So here, the post condition should be less complex than the function, but it should not be trivial. All right, so for the evaluation, this is just a quick formalization of the problem. So this first definition here is just an example, is an instance of natural language description of the problem, the reference implementations of the code, and the test set, which is part of the data set with the code, and it's just the regression suite on that specific problem. An evaluation of an expression is just an assignment of the values of S, the state, for the variables in the expression, and then we evaluate that and we get the result. So for the first one, which is correctness, for every test in the test set, for every input in the test set, the evaluation of the post condition on that input and the reference, and running that input through the reference code, so the output. So the post condition evaluated on the input and the output should be true. So it should, all inputs should be true for the post condition. For test set completeness, it's a little bit more complicated. So here it's a fraction. So this is a score. It's not just every test has to be true. It's a score. So it's the fraction of mutants. So CM is the set of mutants. It's a fraction of mutants where at least one test evaluates to false with the post condition. So the post condition should catch the mutant using at least one test. And we can also extend this to be for a set of post conditions. So the LLM may generate 10 post conditions, and then we check if any of them catch all of the mutants. All right, so for the testing, they use GPT-5 and GPT-4, which are chosen for their coding ability. They also use StarChat because StarChat is open source and it allows the results to be easily replicated because I'll talk about that a little bit in the limitations, actually. For the datasets they use, for the test set correctness, they use eval+, which is 164 Python problems with documentation, tests, and reference solutions. And these are all manually created and annotated. And this is an extension of the human eval dataset. For the test set completeness, they use LLM-generated mutants. So they create both natural mutants, which are bugs in the LLM implementation naturally, and artificial mutants, which are specifically asking the LLM for bugs if there aren't enough natural mutants. And they create an average of 55 mutants per eval+ problem. And they also made this dataset open source, which is nice. They also use defects4j, which is used for testing on real-world examples, and it's Java bugs dataset, and it's historical bugs. All right, so for the results on test set correctness, GPT-4 achieves a 96% problem coverage after 10 generated post conditions. So how many of the problems after 10 post conditions do we have correct post conditions for? 77% of GPT-4's first try post conditions are correct, and StarChat overall does very poorly, actually. They do okay after 10 post conditions, but after one, the results are not good. They also find that natural language alone is sufficient for correctness. The LLM does not need the reference code. And they also find that simple prompts leads to more correct post conditions by a small amount, about 5%. So yeah, cool. All right, so for completeness, GPT-4 discriminates 81 to 85% of mutants on average for every problem. And so the data is a little bit weirdly presented in the table that they give. So the first data column is the percent of the percent of post conditions that are bug complete. So out of all of the generated post conditions, how many catch every mutant for a problem? The second column is the percent of problems with at least one bug complete post condition. And the third column is the percent of problems with where all the post conditions are unionized. There's a union of all of the mutants caught by the post conditions, and if all the mutants are caught, then that contributes to that score. I would say the most important values here, or the most important columns, are the union bug complete columns and the natural bugs bug completeness score. And we can see that GPT-4 does the best on these two. And I also want to say that having 100% here is not necessary or guaranteed or even desired typically. Like you're not always going to have 100% bug completeness score, just because sometimes you just can't represent every single case, you can't capture every single mutant in a single post condition or a set of post conditions, although higher is definitely better. So here we see that there are actually 30% better results for base simplicity. And this is probably because the simple simplicity results in more correct post conditions, but it has less discriminative power. It catches less bugs because they're simpler. But because they're simpler, they are typically more correct. And here they filter the results by correct post conditions. We also see that there are slightly higher scores with the reference code included, and this is probably because the LLM is just able to re-implement the function itself as the post condition. All right, cool. They also do some qualitative analysis on the generated post conditions. So they annotate a bunch of post conditions. I think it was like 900, and they categorize the prevalence and the average bug completeness score. So here we can see that the type check is the most prevalent, with 47.4% prevalence of all post conditions, but it also has the lowest average bug complete score, with 14% on natural bugs. And so this is kind of actually an excuse for StarChat's low completeness score, because StarChat actually mostly generates these type check post conditions. And this can also partially be explained by the type hints in the eval plus dataset. Typically we wouldn't have those. We just have explicit typing in any language that's not Python, any type language. But we're in Python, so the LLM might see these type hints and then be like, okay, I'll generate a type check post condition because it's the obvious choice there. And we can also see that the highest bug complete score is arithmetic equality, and this is something we'll see in the demo too. So that's cool. Actually, we see bounds in the demo, but the bug complete score is pretty high for the bounds too. All right. So for the real world testing, we can see that. Recall that Defects4j has 840 methods. So Defects4j has a lot more bugs typically, but they had to reduce the size to be compatible with their natural language to post condition tool, because some of the bugs were in way older versions of Java that don't accommodate their tool. They also greedily include other methods in the prompt, because they realized that the method in isolations sometimes or often wasn't enough for the model to understand what the post condition was actually supposed to be, like what the method was actually supposed to be doing. Anyways, that said, GPT-4 ends up discriminating 9%, so 47 bugs out of 525, and this is after 10 generated post conditions that compile. Yeah, cool. Okay, and then there's also a total of 64 bugs caught across all prompts and models. All right, this doesn't seem amazing. It doesn't catch all of them. It's not like a really high percentage, but we will see compared to the baselines how it actually compares. So let's start with Toga. So Toga generates test oracles for a method. So test oracle is basically a predictor for the output of the test, and if it conflicts, then we can assert that the test is there's something wrong with the implementation. And so here it takes Toga takes a test prefix and it generates an assertion or an expected exception. And this is a machine learning generator, a test oracle generator. So the differences between TOGA and natural language postcondition are pretty varied. So TOGA assertions can only be applied at testing, right? Because they're for the test oracles are for a specific test prefix, and so they can't be applied at runtime, whereas natural language postcondition postconditions can be. Also, TOGA can only generate equality postconditions, which we saw we had really high bug completeness score. But natural language postcondition actually can do any Boolean expressions, which kind of expands its range, its capacity. So the results here is that TOGA catches 42 out of the 525 defects4j bugs. So that's pretty similar to the results of natural language postcondition, but it actually turns out that only 5 bugs were caught by both approaches. So they're highly complementary, and this is partially explained by TOGA not being able to reach certain bug locations if the test doesn't, access those. Also, TOGA can handle exceptional bugs, but natural language postcondition can't in its current state. And also, TOGA can use objects from other classes and methods, whereas natural language postcondition also can't. So this is mostly limitations in natural language postcondition and less, feats of brilliance by TOGA. All right, so the second baseline is DICON, and DICON infers invariance through multiple program runs with the test suite. So you have the regression tests, you run the code, the method a bunch of times, and DICON kind of infers, okay, these are the invariants that must remain true before and after execution. So invariants with DICON are always implementation consistent because they're inferred through the test suite runs. And DICON also doesn't generate tests from natural language, it generates tests from running the code. Okay, so for the results, the DICON was tested on the 101 bugs caught by natural language postcondition and TOGA, and the the authors state that this is because it's difficult to test with DICON. So DICON generates 78 correct postconditions out of the 101, and the ones that were not correct either timed out or DICON just failed to generate them. And out of these 78 correct postconditions, only 3 sets of them caught bugs. And this is very low. So it's a very low bug discriminating ability, and this is because DICON tends to overfit on the regression tests. All right. So let's just go back a second. So we can see that overall natural language postcondition performs better or equal to these baselines, and so we can see that the tool is effective. All right, so for some related work, in specification generation, specification generation is a comprehensive description of a program's intended behavior, and these vary in formality. So you can have, inline document or inline comments, and you can have postconditions, unit tests, whatever. So from code, there's static and dynamic analysis, of course. There's also abstract interpretation. And then from natural language, we have named pattern matching, text normalization, this tool, natural language postcondition. However, the tools that are existing are not extensible, so they don't they don't generalize to other languages easily or typically. And they also require a semi-structured format of the input. All right, so for machine learning for specification specifically, we've seen DICON and TOGA. There's also Athena test and TyCoder. So DICON, TOGA, Athena test, and TyCoder all depend and generate tests. They are all about generating tests or generating things that are specific to a set of tests or regression tests. EvoSpecs is more like natural language postcondition in that it infers postconditions more generally, and it actually does this using the test suite, but it doesn't overfit the test set basically. And there's also several other emerging methods. EvoSpecs is actually it's not meant to find bugs. It's meant to infer postconditions and infer things about the methods themselves. And so natural language postcondition is unique in that it tries to find the bugs. So there's several other emerging methods that are pretty promising. And I think it's important we talk about new LLMs a little bit. So there's GPT-5 Chat, which is the newer one that was released this year, I believe. And it has a coding average of 78.57 versus the GPT-4, which was the best performing model that they used on average, which has a coding average of 37.31%. And so new LLMs have not only better coding abilities, but also much larger context windows. And so remember how in deflex4j they had to fill the context with the rest of the code base? This is going to be much easier with these newer models. So it'd be interesting to see ChatGPT 5 applied on this problem. All right, so some of the limitations of the paper that the paper actually acknowledges is that LLMs are black boxes. There's no interpretability, very little. Also, LLMs are closed source models often iterate, and prompts and results can become obsolete or degrade in performance because there isn't really a lot of stability there in these closed source models. There's also possible data leakage with the training sets being in the training data for the LLMs, but they're actually, as I said in the beginning, there's limited training data on this problem specifically, so that's a little bit nulled. Also, the generalization of the findings was not completely evaluated. They only tested it on Java and Python, not other languages, although the tool is supposed to be usable on other languages. So that's one of the another limitation. And finally, the measure of completeness, the bug completeness score, depends on a set of LLM-generated mutants, which is possibly biased. It's possibly just a small subset, possibly like very easily findable bugs of all possible mutants. So their completeness score might be completely wrong. Okay, so some of the limitations that were not acknowledged by the paper is that we can't always iterate until we have a correct postcondition, especially on small-scale projects. In larger projects, the context actually might be far too large and interconnected to fit in the model's context window. Now, this is a bit, stifled from ChatGPT 5's much larger context window, but for like one-shot applications, this might be a problem. Also, natural language to postcondition was only tested on relatively simple and self-contained functions. So in the defects for dataset, they had to include a bunch of other classes and methods, but also this is kind of like a unit test generation of postconditions. It's very much on single methods, and it would be interesting to see this applied on end-to-end or integration tests, so through multiple methods, postconditions on those. Also, in my opinion, DICON was poorly tested. They kind of did DICON dirty with only testing it on the 100 subset tests that natural language to postcondition and Toga got correct. Also, there was no discussion at all of runtime overhead for postcondition generation, be it in time or money expenditures or tokens cost or whatever. So that was generally, I found that kind of lacking. All right, so in summary, this was a feasibility study of LLMs for natural language to postcondition. They came up with some novel metrics, and they also found that LLMs are actually adept at translating natural language to postconditions, and they have high discriminative power. So we found that there's 96% correctness for these postconditions, and they have an 81% discrimination power on the dataset that they used. And they also caught 64 real-world bugs, which is solid. And they also made the artifacts open source, so they made the dataset open source and the code. And they overall highlight the possibility of LLMs acting as a bridge between informal natural language and formal code specification. All right, thank you. Any questions? All right, so this is just a quick demo on the eval plus dataset. The defects for dataset is not public. Also, it's not going to be an evaluation of any of the prompts because I need Docker to run that, and that's just too clunky for an in-class demo. So what I'm going to do instead is I wrote a quick script to visualize the generated postconditions next to the eval plus problem, and I've chosen an eval plus problem that should be pretty straightforward to generate or to look at the postconditions for. So what we're going to do is we're going to generate a postcondition for the simple prompt with no reference solution, and we're going to generate a postcondition for a base prompt with reference solution. So let's start with the base prompt, or the simple prompt with no reference code. Cool, and for this I'm using GPT-4. Now let's change this to be the more complex one, so base and including the reference code just to see if there's a difference. Let's run it again. Cool. So we should have two answers here in the LM Gen outputs for 1609 and 1625. Cool. So let's pre-process the data. I have it somewhere here. Yeah, there we go. We have to change the YML file. So let's start with 02 1609. So again, that's the simple one. Sorry, yeah, the simple one. Cool. And then let's do it for 02 1625, and that's the complex one. Cool. Okay. Now let's run my quick visualization script. So our generated postconditions are here. So 1659 and 1710. So again, it's the simple and then base. So let's start with response pre-process outputs 2025 1102 02, 17, 10. That's fine. And then let's run that again with the base simplicity. So that is 02. Oh, okay, sorry, I did the simple one first. But anyway, so 02, 16, 59. Oh, okay, looks like I didn't do it right, so let's see. Oh, okay, I didn't write the entire one. Sorry about that. So 1659 and then pre-processed samples.json. Okay, let's do it again. 02, 17, 10, pre-processed samples.json. All right, cool. So now we can go to our post-condition visualizations. We have again the simple one and then the base one. So let's start with the simple one. So this truncates a number, so it just returns whatever the number is after the decimal point. And so we can see that the post condition here asserts that the return value, it's an equality assertion, and it asserts that the return value should be between 0 and 1, which is a fantastic post condition. Yeah, it's good. It sounds good. We can see that the leftover part is always smaller than 1. It's in the docstring, so it probably got that from that. Then we can see the more complex one. Again, did the same post condition. So we can see that sometimes they do make the same post conditions, even though there's different inclusion or not inclusion of the reference code. Yeah, thank you.